Okay, hello.
So please welcome Benjamin Solomon, who's going to be telling us about Soliton cellular automata.
Firstly, I just want to say thank you to the organizers for putting this all together, as well as for everyone being here in person. It's been lovely to attend all the talks and listen to all the people. So thank you very much. Okay, so today I'm going to be talking about Soliton cellular automata for the affine general linear Lie superalgebra. This is a joint work between myself and Mitchell Ryan. Okay, so the goal of the talk is to first go through a description of the box-ball system, and we're also going to look at solitonic behavior within this system. We're then going to go over a brief description of crystals and how we encode such a system using crystals. I'll then go on to describe our generalization of the system and solitonic behavior that we find in that system. Okay, so the first question is, what is a box-ball system? So the box-ball system is an ultradiscrete analogue of the Korteweg Vries equations, which is a nonlinear partial differential equation. And so we obtain the box-ball system by making this ultradiscrete, which means it's discrete in both time and space. And you might know that the KdV equation models water waves in one-dimensional channels. So within the KdV equation, we have what are called soliton solutions. And these are seen as solitary waves that propagate throughout the channel. So I now have an example of, this is a state within the KdV solutions of two solitons. We see one is higher amplitude and one is lower amplitude. One of the properties of solitons within the KdV equation is that they move with speed proportional to their amplitude. So we'll see as the time evolution of this system occurs, we'll see they'll go through a collision period and they separate out and continue to propagate. So the important properties we're looking at here are the fact that they are stable under collision and that they move with speed proportional to their amplitude. Okay, so the box ball system is a finite number of balls in an infinite line of boxes. And we describe the time evolution via a simple algorithm where we pick the leftmost ball and then we place it in the nearest empty box to its right. And then we do this for every ball until all balls have been moved once. So starting the time evolution, we have this following state, and we pick up the leftmost ball and we place it in the empty box to its right. We continue doing this for each ball until all balls have moved once. And this is one time evolution of the system. Okay, so just like in the Korteweg Vries equations, we also have solitons that arise in the box ball system. So solitons in the BBS are groups of balls that have speed corresponding to length and are stable under collisions. And so you might notice that these are very similar to the defining properties of solitons in the KdV equation. Okay, so here is a state of the box ball system. And we can see we have two solitons, one of length 3, one of length 1. We describe the time evolution as by the previous algorithm. So after one time evolution, we see that they've moved with speed corresponding to length. And they continue to propagate. They go through a collision period and they separate. So again, noticing that they maintain their shape after collision, which is an important property. Okay, so now I'm going to go on to go over a brief intuitive description of crystals and how we encode a system using Tableau. So we'll consider the general linear Lie algebra, GL2, which is the space of 2 by 2 matrices equipped with the commutator. We'll also consider the standard basis vector for the two-dimensional complex vector space. And we have the basis for GL2. And so we have the following relationship between how GL2 acts on this basis. And we can encode this relationship with a crystal, where we can think of crystals as kind of like a label-directed graph. And so we have vertices that index the vector space basis, and we have edge labels that correspond to generators of the Lie algebra. And so we can kind of simplify this by removing the H element, the H generators, and then remove the lowering operator. And we're left with the following crystal for GL2. Okay, so more generally, we can consider any UQ GL2 representation. and we can construct the crystal from the q to 0 limit of the canonical basis. And so this allows us to have tableaux of different shapes, and we can compute the tensor product of these tableaux or crystals using a signature rule. So one problem that we have with crystals like GL2 is that they're not connected under tensor product of crystals, under tensor products. So in order to change this, we utilize the affine Lie algebras. And so these provide us with additional operators, and it means that the crystal is connected. Okay, so now we'll go on to how we encode a system of the box ball system, the box ball. So we have the following encoding. You can see that we have the tensor product of tableau, and a 1 represents a vacuum element, and a 2 represents a full box. And so we've now encoded the state, and we want to describe how we evolve the state over time. And we can do this by utilizing what's called a carrier. And this carrier will pick up balls and place them in their correct places. And so we initialize the carrier as a single row tableau, with the following entries. And then we move the carrier using what's called the combinatorial R matrix. And this is a unique isomorphism between the tensor product of crystals. And this effectively allows us to swap the place of tableau in a tensor product, which is very useful for us. Okay, so here are 2 crystals. So we have the carrier tensor a single box and a single box tensor a carrier. And we use the signature rule to calculate the crystal operators to give the following graphs. And we can see following crystals, and you can see the left-hand side is clearly isomorphic to the right-hand side. And this is exactly the R matrix that we use. Okay, so we have our previous state that we encoded, and we're going to pass the carrier through the state. So we place the carrier at the beginning of the state, and then we apply R matrices to the carrier and each box in the system. And so we apply the first R matrix, and we see the carrier picks up a ball, and then we continue doing this until the carrier is passed all the way through the state. We see it picks up a ball in the correct places and places them depending on its position in the state. And once the carrier has passed through the entire state, we see that we obtain the time evolution. Okay, so there have been many generalizations to this system, and one notable one is called the colored system, which utilizes the GLN affine crystals. And this gives us, we can think of balls of different colors. So instead of just having 2 and 1, we also have up till n. We also have a generalization that had higher height columns. So each state is the tensor product of column tableau. This was done by Automata. And we also have a single box tableau generalization of the box ball system, which utilizes the supersymmetric Lie algebras. That's by Hakame and I. So now I'm going to go on to describe how we've generalized the system using the affine general linear Lie superalgebra. So the general linear Lie superalgebra is a set of linear transformations of the Mn dimensional supervector space equipped with the supercommutator. Given as follows, we utilize the structure of this algebra to describe the supersymmetric box ball system. So we have the standard basis vectors for the Mn dimensional supervector space over which GLMN acts, and we have the crystal for GLMN. And so we denote the barred values as bosonic entries and the non-barred values as fermionic entries. Okay, so elements within our box ball system are given by tableau of shape YR1. And this is given by a column of values of height R, where the entries are given in this list. And this, I'll also note that this is the ordering of these entries. So M bar is the lowest and N is the highest. And so within the system, we also have the definition of a vacuum. And this is effectively the most bosonic element that we can have. Okay, so we compose a state of the super box ball system as a tensor product of the single column tableau. And just like as I described in the previous box ball system, we utilize a carrier to undergo the time evolution. The carrier is similar to the previous box ball system. However, it's obviously height R and length L. And so importantly, we have from Quanticato this UQ-GLMN affine structure, and we also obtain a combinatorial R matrix, just like for the simple system. And we use this to define the time evolution. So as I previously said, the combinatorial R matrix gives this unique isomorphism between the tensor product of crystals. And we can actually describe the action of the R matrix using a modified version of Shensted's bumping algorithm. Also, just to note a few things. So we denote the insertion of I into a tableau X as I arrow X. And we also denote the column reading of a tableau X as the Japanese reading. So for example, if we have the column reading of this tableau, we first read the third column, giving 1, 2, 3, top to bottom. And then the second column, giving 4 bar, 3 bar, 2. And then the final column. So this is the column reading of the following tableau. Okay, so I'll go through an example of insertion. So we're inserting 2 bar into the following tableau. And so in this example, we're doing column insertion. So we begin by inserting 2 bar into the first column. And we have to look at the entry that we're inserting into the column and whether or not it is bosonic or fermionic. This changes how we do the Shenstedt bumping algorithm. So since we have a bosonic element, we're looking for elements that are greater than or equal to 2 bar in this column. So the first element this occurs for is 2 bar. So we swap the elements and then we begin inserting 2 bar into the next column. Again, this is bosonic, so we look for a value that is greater than or equal to 2 bar. This is 1. So we swap them and we begin inserting 1 into the third column. Now we have a fermionic entry that we're inserting into the tableau. So we look for elements that are simply greater than this value. So 2 is greater than 1, so we insert 2 into the final column. 3 is greater than 2, and we insert 3 into a new box in the fifth column. Okay, so we have an important result from Quanticato that we use to describe the time evolution and the propagation of the system, where Quanticato says that the tensor product of tableau, if we have the tensor product of tableau x tensor y, then the combinatorial R matrix sends n x tensor y to y tilde tensor x tilde if and only if the column insertion of y into x is equal to the column insertion of x tilde into y tilde. So now I'll go through an example of this. If we set the following tableau, we want to check whether or not the R matrix applied to x tensor y is equal to y tilde tensor x tilde. And we do this via the column insertion. So we insert the column reading of y into the tableau x. The column reading of y is given by 3 bar, 1, 2. And we begin by inserting 3 bar into the tableau. I won't go through all the bumping in the essence of time. So we obtain the following tableau after we insert 3 bar. We then insert 1 via the process, and then we insert 2. And we're left with the following tableau. So we now want to check whether or not the column insertion of x tilde is equal to y tilde. And so we have the column reading of x tilde, which we previously calculated, and we insert this into y tilde. And I'll skip the details, but we find that they are equal. And thus we can conclude that the R matrix applied to x tilde y is equal to y tilde tensor x tilde. Okay, so now I'll give an example of a state within the Boxable system. So this is the height 2 state with m equals 2 and n equals 2. And so we describe the time evolution of the system exactly the same as how we described it in the simple Boxable system. So we pass a carrier through the state utilizing the combinatorial R matrix, and we see the time evolution as follows. 2 objects go through a collision period, and then they separate out. So as you notice, these objects have very similar behavior to the solitons we saw in the simple Boxable system. And so here we have a length 2 soliton and a length 1 soliton. And so we're interested in what exactly are the properties that are required of these objects in order for them to act solitonically. As in here? I don't think it's a typo. Yeah, so during the collision process, we we can sometimes lose some things, but they come back if they're solitonic. So yeah, this is quite a complex example of a collision. Anyway, so I'll first talk about what are the conditions of these objects in order for them to have correct speed. So solitonic behavior means that the object will move with speed corresponding to length. So if we have the following object, which is the tensor product of S column tableau, we first impose that it's increasing top to bottom. And so this is weakly increasing if the values are fermionic and strictly increasing if the values are bosonic. And then we also have the restriction of it decreasing row-wise. And this again is strict if the values are fermionic and weak if the values are bosonic. And so the important restriction now is that we're able to draw a line through a column and partition the object such that entries above this partition are less than m minus r bar, and entries below this partition are greater than or equal to m minus r bar. So if the object satisfies these properties, then it will move with correct speed. Okay, so now I'll talk about the main theorem. So now we're considering what exactly are the properties that are required for the solitons to collide correctly, so to maintain shape after collision. And so if we have S and T as by the previous slide, and we draw the line directly above the last row, then S and T will be stable under collision. So here is an example for GL42 with a height 3 tableau. So if we draw the line directly above the final row, so that means that for this particular example, we have m minus r is equal to 1 bar. So as long as the entries above that partition are less than 1 bar, and the entries in that final row are equal to 1 bar, then we will have that this object collides stably with other objects that satisfy this theorem. And so here is an example of an object that does not satisfy the theorem. Here we can see that we must draw the partition above the second row. And so we have that it doesn't satisfy the assumptions of the theorem. And so this doesn't necessarily mean that an object like this that doesn't satisfy the assumptions of the theorem won't behave solitonically. But in this case, this object definitely won't, since we have the 1 value, so it's not strictly decreasing fermionically. So this tableau won't behave solitonically. Okay, so that finishes up the main part of my talk. And I'll just go through some possible connections between other parts of math and our results. So there's a super analog to the K to B equations. Is there possibly a relationship to our system and this super analog? There's also a relationship between the KP hierarchy and the box-ball system. Is there a relationship between the supersymmetric KP hierarchy and our box-ball system? It's also the possibility of connection between the supersymmetric Heisenberg speed chains and also the total lattice. All right, thank you, everyone. That concludes my talk.
Thank you. Thank you for a lovely talk.
That's all good.
Are there any questions? So I have a question.
Yep.
Can you do all this for the orthosymplectic superalgebras? Has anyone looked at that?
I don't think we've looked at it, but the result of our research heavily depends upon the KR modules for type A. So it's possible that we don't have the structure to do it for those algebras, but I'm not sure. I haven't looked into it.
Because there is an insertion
Okay.
that will work. There's the Burl insertion for the symplectic, the algebra.
Okay, cool. I'll
Yeah.
definitely look into that. Thank you.
Thank you. I think we have a, yes. Thank the speaker again.